I'm back. All right. Set up a conference call. Somebody and I totally forgot about them. So sorry about that. So, anyways, these PM interaction diagrams, right? How they interact together. The axial load and moment, they obviously affect each other. We talked briefly about the mechanics there, and then yeah, and so we talked about this area right here of your PM interaction is like a axial, a beam, sorry, and column with moment, and this right here would be a beam with axial load, right? And the whole idea, I mean, is just understanding that they interact. The axial load and the moment capacity interact, and you read these things by, or the way you use them is you plot your PU and your MU, and if you're inside the curve, you're okay. If you're outside, you're bad. Okay, so ACI requirements. Okay, there's a packet on D2L that has all of the associated sections in there. And then we went through this discussion. Here's the equation. The difference is we got this alpha out front that we talked about just a few seconds ago, and then you obviously have a phi factor, same phi factors that are used in beam design. It's just now we can be over here on the left-hand side. You're actually on compression strains, and so there's no warnings, and so you get 0.65 and 0.75. Okay. There's also a limit of how much steel you can include. There's a lower limit and an upper limit, right? And we talk about our longitudinal reinforcement ratio. That has to be between 0.01 and 0.08. Right? And then they have a minimum number of bars that you have to include in your spiral or rectangular members. Then we said, okay, well, how do you go about designing this? So then that's setting up, you design that thing for strength. Then you have to come back and design the stirrups as well, right? Or the ties as well. And so it's very prescriptive. We're going to do this in an example today, but it's very prescriptive on how you go about designing the ties, right? It's straight up tells you, right, clear spacing, where you have to check your clear spacing, the center to center spacing of the ties, right? You basically calculate this, you have the smallest diameter, and then it's the smallest of all of those things. The diameter of the bar just depends on the longitudinal reinforcement used. If it's number 10 or smaller, you use number 3s. If it's 11 or bigger, you use number 4s. Okay? You can also use wires. And then how you have to satisfy these things, or what these things have to satisfy, are you have to satisfy every other bar has to be tied. Every other bar has to be tied. No bar can be more than 6 inches away from a tie. It only counts as being tied is if it's in a corner like this. You could put these guys around it to pick up the extra bars if this distance right here is greater than 6 inches. And then another way you could do it is put in these J hooks, right? And then you can also put interlocking ties like that. Okay, so then, like I said, very prescriptive. The spiral stuff ends up being a little more complicated. This is where we left off last time. This is covered in 25.7.3 of ACI. And then what we're going to be doing is picking the size, right? The two things at play here is what size is our spiral, what bar size is our spiral, right? And then what is the pitch between it? What is the spacing, center to center spacing? That center to center spacing, actually, let's just write that on there instead of having just that thing. The center to center spacing is what we're going to call the pitch. We're going to call it S, and that's the pitch. Okay? That's the distance in between the spirals, the center to center distance between the spirals, which is different than the clear spacing between the spirals. The clear spacing between the spirals, again, you would have a little slight uphill to it like this, right? Because it's going around in a spiral, right? This distance, right? That distance is the pitch, right? And then this distance here is the clear. Okay, in between those spirals. Okay, and so one of the requirements, the spirals shall consist of evenly spaced continuous bar wire with clear spacing of 4/3 the diameter of the aggregate. So the spacing has to be bigger, a third greater than the diameter of the aggregates. That's just making sure that the aggregates can fit in between the bars, and then not greater than 3 inches, right? And the idea behind that is it's just not going to be effective if that spacing is greater than 3 inches, right? If it's spread way out, well, it's not going to be effective at tying that reinforcement. Okay, so then the other requirement is there. And that tells you a minimum size of the bar that you have to use. The other requirement is that the volumetric spiral reinforcement ratio, so not the longitudinal, but the volumetric spiral reinforcement ratio shall satisfy this equation right here. Okay, so this is a requirement. And we'll talk about what rho S is in a second. Okay? And so it says this is going to be a property. This is going to be a property of our column. Okay, and it just says that this property has to be greater than this value. Okay, and it's very empirically based, but it's straight up. You have a minimum amount of reinforcement that you have to include. Okay, and we should be very familiar with this at this point, right? But again, the idea is if you really want to get the benefit, you have to meet at least these requirements right here, and we'll talk about what these variables are in a second. Okay, and then it puts an upper limit on what your yield stress could be in your reinforcement there. All right, so. And then it also says that you have to have an extra turn of spirals near the ends, and so right here it's saying, oh, you got to double up the spirals down here at the bottom. And then up at the top, you would have double spirals up at the top as well. Okay. All right. So what is this rho S value? We said it's a property of our column. Okay. And what it is, right? Just like longitudinal reinforcement ratios, the longitudinal reinforcement ratios were the area of steel divided by the area of concrete. And what this is the volume of steel. This is volume of steel over pitch. Now let's make a little bit more room. 1 pitch has to be, or that divided by the volume of concrete over 1 pitch. Volume of the core. We'll say volume of the core. Yep. That's more clear. And I'm going to move this guy. I can do this like that. Nice. Over 1 pitch. Okay, and so it's the volume of steel divided by the volume of concrete. And so that's why it's called a volumetric reinforcement ratio, right? Because it's the volume to volume as opposed to an area to an area. Okay, well, how do you calculate that for a beam? And that's what this is doing. Okay, so what this is the area, this is the volume of steel over 1 pitch, and this is the volume of concrete over 1 pitch. Okay, and so if you think about what's happening, and let's look at this. Well, we'll define these terms down below. But what this is the bar area that's the bar area of your spiral. That's the cross-sectional area of your spiral. So it's like, here's my spiral going around. It's the cross-sectional area. So if I was looking at this, it's just the area of a bar, right? So if it's a number 3 bar, it's, what is that? 0.11 is, you look that up in the table. If it's a number 9 bar, it's 1, right? It's just the cross-sectional area of 1 bar. And then if we look at this pi dc minus dB, okay, so this is the diameter basically of the circle that's going around. So you take pi times the diameter, right? That gives you the circumference. If you take the circumference, so that gives you the circumference of this. If you take that circumference and you multiply it by this area, it would give you the volume. So it's like, it would give you this volume of steel around 1 pitch completely, okay? And then this guy right here, this is just the area of a circle, pi dc squared over 4, right? That's the area of a circle, right? So it's the area of this circle going around like this, okay? And so you take the area of that circle and you multiply it by the pitch. And so you're taking that, and then, so you take this area of a circle and then you multiply it by, right, into the board 1 pitch, and that gives you the volume, right? And so it's the volume of steel divided by the volume of the core concrete, okay? And so in these equations up above, just to finish this off, the AG is the gross area of the concrete. right? It's pi DC, the pi d squared over 4 for a circle, right? And then it is, I'm going to move this, I want to put it on the way, yep. So it is it's pi d squared over 4 if it's a circle, and it's b times h if it's a rectangle, right? This ACH is the area of the core. Right, which is pi dc squared over 4. Okay, we'll talk about what dc is in a second. FYT is the transverse yield ratio, or the spiral reinforcement, or spiral yield stress. Right, think about that T meaning the transverse reinforcement. This is bar area, cross-sectional bar area. Right, this DC, diameter of the core, out to out diameter of the core, out to out. Of core, right? So put it on this drawing over here. It would be, I don't want that color. Right, that distance, that's DC. Right, if we look up at this equation above here, this DC minus DB, what that does, that puts you at the center of the bar, right? If you do DC minus, right, if you did DC minus half of this bar diameter, that puts you at the center of this bar. And then on this side, you'd be this minus half of a bar diameter. It would put you at the center of this bar that's going around. And so what this does, all this DC minus DB does, because you do half on one side and half on the other side, that just puts you at the center of this, as opposed to going the out to out. And so they're narrowing in on this thing, right? They're sharpening their pencil a little bit. If you want to figure out the volume of steel, you want to go from the center of that circle as it goes around, as opposed to the outside of the bar as you go around. It makes very little distance, I would assume. There are very little difference, that is, okay? But then the DC is that distance right there. And then what is DC, though? This is this distance here. How would you calculate it? This move that lines up right. That's the overall diameter, right? That's the overall diameter. But then this distance right here, this is the clear cover. And so typically for a column, that clear 1.5 inches, right? And so you'll have on this other side here, you'd have the same thing. You'd have a clear 1.5 inches. And for columns and beams, that's what your clear cover is. And so your DC would simply be the diameter minus 3 inches. Okay, for a typical column. Okay, and so yeah, hopefully that makes sense. Okay, again, let's just finish this off here. This ends up being diameter of the bar. Okay, and again, that's important because that puts you at the center, right? That puts you in the center of the bar right there. And then S is the pitch. We've already defined that pitch, right? And this is center to center. Okay, so this one's a little bit more involved doing the design of this, okay? Maybe that's not actually the design at this point, right? The design Right, we'll talk about that in a second. This is just a requirement, right? We didn't say, well, how do you go about designing the spiral? Here it's very straightforward. This is what you do. Boom, 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 boom. That's how you do it. This one, it just says like, oh, look, we have to use, we can't be greater than a 3-inch pitch. Okay, there's a minimum that you have to use, and oh, by the way, this thing that we calculate for our beam has to be greater than this. Okay, and just real quickly, how you design that, right? The things that are, right, the bar size is going to matter, right? The area of the bar. So if you increase the area of the bar, then rho s goes up. If the area of the bar goes down, then rho s goes down. And so that's one thing that controls. And then same thing with the pitch. If the pitch gets smaller, rho s goes up. If the pitch gets bigger, rho s goes down. And so those are the two things that we have control over, right? Everything else is kind of the diameter of the core, and the diameter of the core is kind of set, and that comes from the design for axial load, right? But then this guy and this guy are what we have to play with in order to make sure that this is bigger than this. Right? And so the idea is usually they're very similar to what we did for shear design of beams, is we assume a size, so maybe assume a number 3 bar here, right? And then you solve for the S. You set this guy equal to this guy, and then you solve for that spacing. If that spacing ends up being really, really tight, then increase this, and then solve for the spacing again, okay? And you'll get to do that in a homework in a little bit soon. Okay. So those are all the requirements. Okay. So then I put together a little document about the design. We haven't really talked about design, right? I guess we talked about what the equation is for calculating the capacity, right? But we did not say, well, how do you go about setting the dimensions of our beam? How do you go about, we did just briefly talk about the design of the spirals after you come up with the size and the number of bars that you use and things like that. So I put together a document. Column design procedure, concentrically loaded columns. Okay, so then it takes you I'm really proud of this. I think this should be pretty helpful for you guys. So what it is you want to make sure that your PU is less than phi PN, right? And so here's the main equation, right? It is alpha times phi, right? The alpha is in there to account for accidental eccentricities. The phi factor is your typical phi factor. And then you multiply, that's the ACI equation for your capacity, okay? And then I put in here what alpha ends up being. It's 0.85 for spirals, 0.8 for ties. I put in what phi is, 0.75 for spirals, 0.65 for tie, okay? And then area of steel is a total area of steel for the entire cross section. Fy is the yield stress of longitudinal steel. F prime C is the concrete compressive strength, and Ag is the gross area of the concrete, which is B times H. Only for, we should say that. That's an error. I shouldn't be too proud of this. It's not, this is for a rectangle, right? It's not that for a circular column. So I need to fix that. I'm going to fix that. Okay. Okay. So then how do you do this? Step by step, this is how you go about doing it. You factor your loads and determine what PU is. Okay. Decide if you're going to use spiral or tied. If you're going to use spiral or tied reinforcement. Typically, if you have a rectangle you go with ties. If you have a circle, you go with spirals. That's the kind of standard, and that's kind of what we're going to stick to in this class. And the problem statement will probably tell you which one to use there. Okay. Depending on whether or not the column dimensions are known, sometimes the dimensions are predetermined by architectural purposes, or the problem statement says so. The design procedures follows one of the following paths. Okay, do you know the dimensions of the column? Do you know what AG is? Okay, if those are known, what you do is you come up here and you said, I set PU equal to phi PN. So you come into this equation, PU is equal to phi PM, and the only unknown in this equation, since you already know the dimensions, you know what AG is, and you know what alpha and phi are, and you know what PU is, the only unknown is that area of steel right there. And so you set PU equal to this, you solve for the area of steel, and then once you have that area of steel, you have to select your steel, okay? And then after that, you check to make sure that you're within these limits, right? Is your area of steel, or your area of steel divided by the gross area, is that greater than 0.01 and greater than and less than 0.08. And if you've done that, you're ready to move on to the next step. All right, so that's that. If your column dimensions are unknown, right? So you don't know anything about the column dimensions. What you do, again, is you set Pu equal to phi Pn in the equation above, and then you make an assumption on what rho g is. And you remember we talked about longitudinal reinforcement ratios being helpful for the design of things, right? And so you assume a rho g between 0.01 and 0.08. The requirements are that it has to be between those two, okay? And so we assume something in between there, right? You could start out with 0.035. I think the example we do today, the problem statement specifically says start out with the rho g equal to 0.04, right? You take that, and then the definition of what rho g is, right? Rho g is the area steel divided by Ag. You kind of flip it on its end here a little bit. And you say, well, the area steel is rho g times the gross area. What you do is you take those terms and you substitute them in to this equation up here, right? And so this right here, everywhere you see area steel, you put rho g times Ag, right? And the same thing right here, you put rho g times Ag, right? And when you do that, it gets you down to one unknown, and the one unknown is Ag, okay? And like I said, we'll do this in an example in a little bit, but that's the only unknown that ends up being in that equation up above. And then you solve for the Ag. Once you have that Ag, you know what gross area your column needs to be, about what it needs to be, okay? And so then obviously that's going to be, it's going to be some weird number, right? And so you get to pick a B and an H. You're going to use whole numbers, right, or half-inch numbers or something like that. You're not gonna have your column dimensions being 0.756 inches or not. Oh, that's a terrible dimension. So 10.25 inches or something like that. It's going to be 10 inches or it's going to be 12 inches or something like that. Okay, so you'll pick your column dimensions. Okay, and then at that point you now know your column dimensions. Once you know your column dimensions, you come up here and you do this, okay? You know, up here, and then you start over here. So now we know our column dimensions, and you go through these steps, and then you'll design your steel, okay? And then the very last step, if you make some assumptions in here where you're starting to change dimensions and you're not sticking to the rules specifically, it's okay, as long as at the very end your Pn is greater than Pu. As long as that happens, you're okay. And then the last part is you have to design the ties. Now you know your dimensions, how many longitudinal or what your longitudinal reinforcement detail is going to look like. Now you got to pick out your ties or spirals, right? And I basically took those rules from the last pages of notes here and said this is how you design your ties and this is how you design your spirals. Okay. I guess maybe one other thing to say here. Right? We kind of talked about the design of these spirals. Let me formalize it here. What did I do there? Yeah, we're going to do an example in a second. All right, for the design. One, we are going to assume spiral size, right? That will determine what A sub S is. Will determine what A sub S is. And above equation. Start with number 3. That doesn't work. Increase size. Okay. So that's the first step. The second step is we set rho S. Rho S property equal to rho S limit. Right, and so in the above equations, what is it? Set 3 equal to 4. Okay. And 3 solve for pitch. Right, which is S. And 4 if less than 1 inch. Okay, about that. Right? Technically, it's the clear spacing has to be less than 1 inch, but I think for this case, it's all right. Increase spiral. So if pit, and I should say this, if clear spacing is less than 1 inch, increase size. If greater than 3 inches, choose 3 inches. Okay, so that's how you would do this last little design of the spirals. Oh, I should probably put that in there. We talked about that before, but that's a good method to do that. If it's greater than 3 inches, it's just meaning that you get away for spacing these things at 4 inches, but right, you get away with spacing them at 4 inches, but you can't. You're only allowed to go to 3 inches, and so just tighten it up to 3 inches, right? And that'd be a conservative estimate. Okay, so that is that. Okay, that's a nice column design procedure. So let's do an example here. Okay, example: design a square tied column with longitudinal reinforcement ratio of about 0.04. So in this particular case, it says, yep, start with this equal to 0.04. Okay, and we're given what the dead load is, right? What the dead load is, what the live load is, what their concrete strength is, and what our material properties are. So we have to factor our loads. That's one of the first things that we have to do, right? So we say PU is equal to 1.2 times PD plus 1.6 times PL. And in this particular case, this ends up being 496 kips. That is a lot. Okay, 496,000 pounds. Okay, but we're going to see that concrete can handle this pretty easily. Okay, and so in this equation, right, what we do is we set that PU equal to phi PN, right? So we set 496. Got my straight lines on. 496 is equal to PU, is equal to phi PN. The phi PN equation is phi times alpha times the quantity of 0.85 F prime C times AG minus the area of steel plus F sub Y times the area of steel. Okay, that is our overall equation that we have there. Okay, in this equation up above, phi is equal to 0.65 because it's a tie, and alpha is equal to 0.8. Right, so these are because it's a tied column. Okay, and then the next thing we have to do, like we said, if you follow that procedure, it says that rho G is equal to 0.04, right? Which this is equal to the area of steel divided by AG, right? That's just the definition of what longitudinal reinforcement ratio is. You take the total area of steel divided by the gross area. And so we could say that the area of steel is equal to 0.04 times the area of steel. Okay, and now what I do is I take this right here and I put it up here for what area of steel is. So this guy goes right there, and it goes right there. Okay, and so then the only unknown, that's times the gross area, rather. Sorry. Right. All we're doing is just taking that AG and putting it over there, right? Or AG putting it right there. That's what the area of steel is. So I wasn't done yet. Okay, right? And so that goes up in there, right? So then now the only unknown that you have is this gross area, right? And so at this point, you plug it in above and you solve for AG. in equation above. Okay, and when you do that, you get an AG equal to 168.9. 168.9 inches squared. Okay, so that's what we get for the gross area required, right? How much concrete is required, or what dimension do we need in order to reach 496 kips with a longitudinal reinforcement ratio of exactly 0.04, right? And so, right, we're not going to make our dimension, or we're not going to nail this thing exactly, okay? But the problem statement said it wanted a square column, so this is just going to be equal to b squared, right? You take the width times the height, right? The gross area, right? This is b and this is b, right? So the overall dimension is just going to be b squared, right? And so we could solve for b. B ends up being equal to 12.98 inches. Okay, and I'm just going to round that sucker up. So that's what you would need in order to get 168.9 inches squared with a longitudinal reinforcement ratio of 0.04. But at this point, we get to pick whatever we want, right? This is just getting us in the ballpark of where we need to be. I'm going to round this thing up to 14 inches. Okay, why? Just because it's an even number, right? 13 is an unlucky number, right? And so we're going to go with a 14-inch column. And so what our actual AG is going to be, right? Our actual AG is going to be equal to 14 times 14, right? 14 squared, which ends up being equal to 196 inches squared. Okay, so that is what our new gross area of our concrete is. So it's a 14 by 14 inch. It's a 14 by 14 inch column, right? And has a gross area of 196. Okay, what you're going to be inclined to do, and it is wrong, okay, so don't do this, is to then just go, oh, I want to finish this off, right? Look right here. It says the area of steel is just 0.04 times the gross area. All right, well, I get away, and I was going to say, I'm going to make this thing 0.04 times 196, and that's the area of steel that I need. No, that's the area of steel that you would need in order to get a longitudinal reinforcement ratio of 0.04. But that's not, right, we don't want to do that. See, what happened is we picked this thing to be 14 inches, so we made it bigger than it actually was. And since the gross area is going to be bigger than it actually was, we could get away with less steel, right? We increased the amount of concrete included, so then we can get away with less steel. And so our longitudinal reinforcement ratio is going to be less than 0.04, right? If I picked this thing to be 14, I increased this thing to 14 inches, and then designed it for 0.04, it'd be including way more steel than we would need it, okay? The other thing, I guess, conversely, if I said, all right, I'm going to round this down to 12 inches, I could have rounded it down to 12 inches, so then I made it smaller than it needed to be. If I did it then, you'd be in trouble if you just multiplied it by 0.04, because then you would have too little steel, right? If I made this thing smaller, if I brought that down to 12 inches instead, if that goes down to 12 inches, then this would have to go up. My longitudinal reinforcement, it says you need 12.98 to get 0.04. If I made this thing 12, my longitudinal reinforcement ratio would have to go up. And so you got to be a little careful of that. So at this point, don't do that. Don't just say, "Oh, my area of steel is just 0.04 times AG." Right? You'll either be overly conservative or under conservative. Okay, or not even under conservative, you'll violate the code if you rounded down here and used that. Okay, so at this point you got to go to the next step, right? Which the next step in the solution we just did this to set the size of it, and then now we know the dimensions. So you come up here and you solve for the area of steel, and so now you come back up, and now we know the AG in that equation. So then we go right 496. 496 is equal to 0.65 times 0.8 times the quantity of 0.05 0.85 times 4 is the F prime C times, now you put in the actual value, 196 is what your AG is, minus the area of steel, plus 60 KSI of the steel, the yield stress of the steel, times the total area of the steel. Okay, and so in this equation right here, so we put in the actual AG here, right? This actual AG we put into that AG in the equation above. And so now that if you look at this, the only unknown is the area of steel. So you solve for the area of steel at this point. And what you get is the area of steel ends up being equal to 5.08 inches squared. Okay, so that is how much steel you would need it to include. Okay. At this point right here, we have to pick the steel that gives us 5.08. And then you have to be careful of how many bars that you use. What you would use, actually, I'm going to do that right now if you don't mind. I'm going to come back here, back here. I'm going to go to structures 2. I'm going to go to beams. And I'm going to grab Alright, I'm just looking here. Yep, this would be a good one here. This. That. I'm going to copy this son of a gun. Make the right columns. I'm gonna put this thing right. I'm gonna put it right here. Okay, so this is what we use for beams, right? And so what this table is right here, right? This is on this axis is the bar size, and this is the number of bars. Okay, and the way what you do at this point is I'm looking for 5.08, right, or at least 5.08, something more than that. Because we have a rectangular column, or a rectangular column, we have to use at least 4 bars. So let's just see if we can get away, and it has to be symmetric as well. So you probably have to have an even number of bars. You definitely would have to have an even number of bars. So you have 4 or 6 or 8 or 10 bars, but let's just make it with 4 bars. Let's see if we can reach 5.08. Would you look at that? Okay, 5.08. So number 10s, 4 number 10s would give me 5.08. Okay, and so that's what our design will call for. We'll say this is 4 number 10s, right? And that gives me an area of steel equal to 5.08. Right? And so we've met that requirement. That's the area of steel required, and this is what we're giving it, 4 number 10s, right? And again, it has to be an even number because it has to be symmetric, and you have to have at least 4. And this table we got out of the beam design stuff. And I'll include this in the notes when I post them. All right, almost there. All right, so now we got to make sure that this is going to be okay, right? It should be okay. We started out with an estimate on what rho G was, but now we got to make sure that now, right, we picked something that wasn't exactly 0.04. We are going to get away with smaller than that. We just got to make sure we're not less than 0.01. And so let's calculate what rho G is. Rho G is equal to 5.08 divided by 196. And that ends up being equal to 0.026. And so then 0.01 is less than 0.026, is less than 0.08. Okay, and so we're good to go. Okay. And so we had to make sure that that was okay, right? So we nailed that one. All right, so the last step is we have to design the transverse reinforcement. Okay, so that's the last thing that we have to do, is design the transverse reinforcement. As of this point, we know what the dimensions are going to be. It's going to be a 14 by 14 inch, a 14 inch by 14 inch column, It's going to have 4 number 10s, and the last thing we have to do is design the tie reinforcement. So the tie reinforcement is very prescriptive. Part A in the design right here, it says number 3 is required for number 10 longitudinal and smaller. Okay, number 3. So we're going to use number 3s. Clear spacing shall not be less than 4/3 diameter. We don't know the diameter aggregate, so we'll skip that one. Maximum center to center spacing shall not exceed 16 longitudinal bar diameters, 48 tie bar diameters, or the least column dimension. So we just write down each one of those. The smallest of those ends up being our spacing, and then all corner bars shall be tied, right? Which will be pretty easy because it's just a square. And so I guess in that above equation it just says number 3s and for number 10 and smaller, or at least that would be required. So we're going to use number 3s. Part B is the 48. It's going to be the min of 48 times diameter of the ties, right? 16 diameter of the longitudinal bars, D sub B, or the least column dimension, which is going to be 14 inches. Okay, and so if you calculate the diameter of the ties as number 3 bars, this ends up being equal to 18 inches. This one ends up being equal to 20.3 inches. And then obviously that last one is 14 inches. And so that is what our spacing of our reinforcement is going to be. It's going to be at 14 inches. Okay, and so, and then you have to tie every other bar. Right, and the last step would be tie every other bar. Or tie every corner, every corner. Every corner bar. And so our final step is to detail it. I want that sucker closed in. Okay. And so we're going to have a bar here, a bar here, a bar here, and a bar here. And our tie reinforcement to hit every corner is simply oh, come on. And there'll be like a curl around there. The code actually dictates how much curl around you get at the end, how big what that looks like down at the end, how much you tie it around the end to keep it from bulging out, okay? But there it is, right? So at this point, you just call it out. You say, we call this thing out. Oh yeah, let's put the dimensions on it. Mm-hmm. 14 inches by 14 inches. Right, this would be something that you would hand to a drafter, for instance, and they would go about drawing this thing up. Or in some smaller companies, you actually are the drafters, right? Or if you are an intern, this might be what you're doing, is drawing up these details. And so you'd call out number 3s at 14 inches, okay? And then you'd call out what your reinforcement is. And this would be 4 number 10s. Okay, and there's our design. Right, in there someplace too, one of the steps was checking the capacity. We're okay, right? Without even checking the capacity, I know we're going to be okay, because we ended up, if you look at this, we made conservative guesses as we went along, right? We chose a beam dimension bigger than what was required. We solved for the area of steel, and we picked exactly that area of steel. And so if you calced it out, you would have VPN equal to PU, right? You have to have at least the area of steel of 5.08, and we gave it exactly 5.08, right? If you got a little weird in your design and you made a couple of assumptions and you kind of got lost in there or something like that, you ultimately got to check to make sure that VPN is greater than PU, and that's simply it. All right. So that's it. That is concrete design, right? This kind of sets you up for future endeavors in concrete, right? There are obviously more a lot more to columns or to concrete than what we discussed today, right? There's axial load and bending at the same time. There's torsion. There's these big giant shear walls with these things called boundary elements. There's slab on grade design. There's foundation design. There's all sorts of stuff, but they all kind of follow the same pattern, the same idea of confusion, basically, right? But the same idea of you look at the mechanics, then there's some empirical equation that we use for the design, and a lot of like feeling around and code based stuff. I always joke that you have to be part of some sort of like brotherhood or sisterhood in order to be a concrete designer. There's all these intricacies of the code that you're moving around in it, and you just get so familiar with it, and then you just become a concrete person, okay? Which is what I do. Okay, I'm a concrete person. So, like I mentioned before, I would love to give a TED talk on concrete construction and design, but I don't think that it would get many views. But anyways, is the world's most used building material. It's a good thing to have as we move forward into this world, right? So a couple more comments here. Couple more comments. Homework number 5. Let's just look at that. I have it due next Wednesday, and the idea there is I want to get it, like I said, I want to complete this stuff. We're not going to lecture on Friday. It's supposed to be a day off for you, so we'll go ahead and count it as a day off, right? And so we won't have class this Friday, but I do have a homework due next week, and again, I'd like to have the exam next Thursday or Friday, which would be, what is the dates there? Next Thursday, the 2nd or the 3rd is when I would like to do that. Okay, and 2nd or the 3rd. So, like I said, I'll do some sort of poll online about when you would like to do this, and we'll or if I got to figure out how to do that and how to reach out to you guys. So, so back to this homework. Right, it's designing a spiral reinforced column. The column must carry an axial surface dead load of 180 kips and an axial surface live load of 400 kips. You got to factor those guys and design a spirally tied circular column with these properties. Now, and then neglect buckling. Right, we're going to neglect buckling throughout. So there, it's the same process that we did before. You find out what that AG is, but instead of it making it b squared, it's pi d squared over 4, and then you solve for the diameter of the spot of the column, right? And then you pick your size based off of that, and then you design the spiral reinforcement. Column, right? Indicate the column size, longitudinal reinforcement to be used in arrangement, and the configuration of the confining steel. So that's going to be your spiral, right? So how do you... spirally tied. And so then how do you design a spiral? You set that rho s equal to the rho s limit. You solve for that pitch, and if it works, check the clear spacing. If the clear spacing works, good. If not, then you got to make some adjustments. And then the next part says, after you design the efficient column described above, the architect approaches you and changes his mind and wants to use a smaller column. I think it's a smaller one. And then, is this feasible? And the idea behind it is, right, can you get away with something that's smaller, right? And I think that you might be able to. I don't remember this particular example, but if you make it smaller, then the amount of steel you have to include will end up going up. And so if you make it smaller, and then you're probably going to be pushing up against that 0.08 limit. And that's all I want you to do. Don't worry about designing the spiral reinforcement and stuff like that, but just look to see if it's even feasible. Is it getting too congested? If you have too much steel required, just do a little quick check on that. So, that's where we sit. I'll go ahead and post this in a few minutes, and then I'll post the updated notes with the added tables that I included. So hope everybody's hanging in there. Give me some feedback if something's not working